Hello everyone, today I want to report our paper to World-Face-Aware Neural Architecture Search for FPGA-Accelerated Edge AI applications. In recent years, deep neural networks were widely used in many applications areas such as computer vision, speech recognition, image classification, and robotics. In many domains, DNNs are now able to exceed human accuracy, although these DNNs are designed to solve different issues and have obtained good results. Each of the models need to be designed by the developer manually, and they require a lengthy training period. If this model does not produce satisfactory outcomes, it will be redesigned and retrained repeatedly until a peak accuracy is reached. As illustrated, the process is time-consuming. In most cases, users usually attempt to solve this computational-intensive problem with large quantity of GPUs. In 2017, Google Brain proposed a process of generating machine learning models. It can be applied deep learning models to a variety of the applications. The controller neural network proposes a child model architecture which can be trained after the child model architecture is trained. Developer can evaluate its performance and quality on the assigned task. The controller gets the feedback to improve and it proposes models for the next round. This process will repeat thousands of times. Eventually, the controller learns to assign high probability to areas of architecture space that achieve better accuracy on a handout validation data set. But Google AutoML provides NAS function which developer paid for, but developer can't export models, and the generated model can only be accessed by Google's API. Not everyone or every company have the same computation resource like as Google. Nonetheless, with limited resource, we need to efficiently exploit the computational power of our cloud computing in a smart way. The challenge here is to design an efficient heterogeneous computing system and leverage the cloud and the hardware such as CPU, GPU, TPU, and FPGA intelligently. Before we continue, I will give a brief background knowledge. Neural network architecture search is a technique for automating the design of artificial neural network. NAS can be seen as a subfield of AutoML and has significant overlap with hyperparameter optimization and meta-learning. The NAS scope is illustrated in figure left. The typical NAS takes into account three different aspects: search space, search strategy, and performance estimation strategy. As the figure right, search space. To define which neural architecture will be presented as output models. In search space, we can reduce the search area for specific application with our knowledge and understanding of these applications. A well-defined search space can even search beyond the region designed by mankind. Second, search strategy. A method or algorithm that describes how to efficiently find a good performed architectures. The search strategy directly affects the whole NAS performance. In this stage, the developer will try to find a balance between shortening the search time and finding the optimal solutions. Third, performance evaluation strategy. There are some metrics to evaluate the NAS performance such as prediction accuracy, inference time, test training time, fewer flops, lower memory usage, and so on. The most popular way is to perform a standard training and validate data set like a CIFAR 10. But unfortunately, this is not only computationally expensive but limited the number of architectures that can be exploited. Many recent researches therefore focus on developing methods that can reduce the cost of the performance estimations. In this paper, we propose an efficient way to search neural network architecture and leverage the advantage of FPGA to provide real hardware latency. A fast and cost-effective solutions. Google NAS is limited to hyperparameter search in a fixed model, and Google NAS didn't take into account the hardware limitations. Instead of taking a long time to pick and train so-called a good candidate repeat based on unreliable estimate, we propose a NAS framework which accelerates the search process by including the actual performance measurement in search process. The inclusion of actual measurement enabled the proposed NAS framework to find candidates based on correct information and reduce the possibility of selecting wrong candidate and wasting search time on wrong candidate. To illustrate the effectiveness of our framework, we prototype the framework to work with Intel OpenVINO and field program gate arrays to meet the accuracy and latency required by the user. The framework takes the dataset accuracy and latency requirement from the user and automatically search for candidates to meet the user requirements. Case study and experimental results are presented in this paper to evaluate the effectiveness of our framework for edge AI applications in real-time image classification. Design methodology. In our distribution server client framework, and we use FPGA to accelerate neural network search process. NAS generate candidate model for training and obtain feedback from the client FPGA framework. After several iterations, it will learn to find the model that has a highest score for the target device. The figure illustrates the reinforcement learning algorithm kernel of NAS. Before learning starts, it initializes a Q table with the initial value. Then, the agent selects action A, get the model's reward, enters a new state ST+1, and update Q table. Layer selection. The main purpose of the neural architecture search process is to train the learning agents to sequentially choose neural network layers. We use Markov decision process to perform layer selection. Speaking more specifically, the purpose of this process is to teach an agent to find the optimal path in a finite horizon environment, to ensure that the agent will be deterministically determined in a finite number of steps, and to maximize the total reward over all possible trajectories. To achieve the goal, we restrict the environment to be a discrete and finite state space S. The figure illustrates the MDP for CNN layer selection. Q-learning. Q-learning is a model-free reinforcement learning algorithm to learn a policy telling an agent what action to take under what circumstances. It does not require models of the environment, and it can handle problems with stochastic transition and reward without requirement adaptation. For any finite Markov decision process, Q-learning finds an optimal policy in the sense of maximizing the expected value of the total reward over any and all successive steps starting from the current state. Reward functions. In reward functions, we define current accuracy CA, baseline accuracy BA, user current latency CL, and user requirement latency RL. In the evolver function, we can realize the reward value which consists of accuracy and latency. In the candidate models, actual latency on a target device, then user's requirement, reward value will increase. If the actual latency meets user constraints, reward will become negative value. Design implementations. OpenVINO toolkit consists of the model optimizer and inference engines. It allows developers to take advantage of thoracic FPGA boards, how to convert a CNN models and develop on FPGA to efficiently obtain the inference times. Here we adapt Intel's OpenVINO toolkit. The figure illustrates the OpenVINO working flow. Firstly, we save the Cafe model to proto.txt and Cafe model files. In the meantime, the OpenVINO toolkit helps to convert a training model to produce an optimized intermediate representations of the model based on the training network topology, weights, and basis value. It also helps to deploy the model on the target platform. This figure shows the overall search flow. First, the server generates a candidate model and trains one iteration after model is trained. It will be sent to the client. Secondly, we use OpenVINO model optimizer to convert a trained model to produce an optimized IR of the model. Input data can be inferred by the FPGA. Third, we obtain fine average inference time and inference accuracy. Fourth, after receiving the average inference time and accuracy, the client will check the constraint. If the result does not satisfy the constraint, then the server will regenerate a new sample model. On the other hand, if the result satisfies the constraint, it will train this model 10 epoch and send reward to the server to update the Q table. Experimental result, case study on CIVA-10. The following table illustrates the CIVA-10's experimental result on thoracic OpenVINO start kit and the DE5A NAND DDR4 Area 10 GX acceleration card for OpenVINO toolkit. Search space is 10 to the 18 power. 10 to the power of 18. Compared with the Baker search, which take 8 to 10 days by 10 NVIDIA P100 GPUs. Our design only takes 4 to 53 hours. Our system used NVIDIA Titan X for training. We use OpenVINO Start Kit and DE5A NAND DDR4 Area 10 for experimentals. The table shows the detailed experimental result according to the equations mentioned previously. We set up Q-learning rate alpha equal 0.01, discount factor epsilon equal 1, epsilon from 1.0 discrete to 0.1 in every step. When epsilon equal 1.0, the server will sample 14 models for training, and the agent will stop when epsilon equals 0.1. After each model is sampled and trained, the agent will randomly sample 10 or 15 models from the replay dictionary and update the Q value. This table is not suggest model under constraint in 15 minutes. In this table, we provide 3 models with low latency and low parameters. Future work. Everyone can easily get a well-trained neural network model for their own applications without developing expensive system. By this system, your data can be protection and safety. Develop a NAS framework with a higher performance and lower performance computations. Such space is limited in human design, layer black. Applying NAS framework is a different field of application in futures. Conclusion. With the proper constraint, we can train a CNN model in 1 day by FPGA, TPU, or GPU. Take advantage of the OpenVINO Start Kit features. Help developers to select the accelerator platform that is best suited for their applications. We are collaborating with the Taiwan Computing Cloud (TWCC) to develop a neural network platform recommendation service. Thank you.